normal molar mass, just the total mass over to the mole, and specific gas constant and also universal gas constant. The others are all the same thing but just different way of finding. Okay, and the ideal gas equation, the PVT behavior for the Dalton's law and Amaker's law, how to find that. So here this will be the equation for how to find the pressure for the mixture, provided you know the final temperature and volume of the mixture, and also the volume of the mixture, provided you know temperature and pressure of the final mixture. Yeah, and then we know that, let's say if we look at like pressure fraction or volume fraction, they are pretty much just mole fraction. Alright, so they are all the same. So in general, everything, all the percentage are all in mole besides the mass version. Then we look at this example. So today we will enter example 3. Okay, so before I start example 3, Jake, how's the timetable next Wednesday?
Next Friday?
Next Wednesday.
Wednesday.
Okay, so here you have the mix. You are given the number of moles, okay, of CO2 and also the air. And they are in a vessel of 1 part and 15 degrees Celsius. So here you can safely assume that these are the properties of the mixture itself, okay, the mixture properties. So volumetric analysis of air can be taken as, so for the air, you have the volumetric analysis. Basically, this is just, so like I mentioned, volumetric analysis is basically mole fraction. So this is to split up the 3.5 kilomole of air, basically, just so that you know how many, out of this air, how many kilomole is oxygen, how many kilomole is nitrogen. So number one, you are asked to find the mass of CO2, O2, and N2, and then total mass. So this one is actually very straightforward because you have the mole of CO2, you have the mole of air, so you just need to further break down the air into oxygen and nitrogen. Then based on the mole, you use molar mass to get mass. Okay, so we look at the mass, the solution here. So simple assumption here. Okay, so like I said, first thing you need to do, you need to break down the number of mole of the oxygen first. Sorry, of the air first into oxygen and nitrogen. Okay, so so number of mole of oxygen is just 0.21 multiplied by 3.5, and nitrogen is 0.79 multiplied by 3.5. Because it's just 25% and 75%. This one shouldn't be any issue. So now you have the mole of oxygen, nitrogen, as well as carbon dioxide. Then, since we know that mass is equal to mole multiplied by molar mass, you can find their respective mole by using the number of mole multiplied by molar mass. So carbon dioxide 12 plus 32, so 0.4. Oxygen 16 times 2, 32. Nitrogen 14 times 2, 38. So then then total mass, you just total them out. So for part 2, you need to find the molar mass of, you need to find the mass percentage of carbon over the total mass. Basically, you want the mass fraction of carbon only, not the whole thing. I mean, not carbon dioxide, just the carbon. But we know that carbon is 12, right, out of that 1 kilomole. So you can actually directly use 12 kg. So 12 over the total multiplied by 100%, you get the percentage by mass. The 100 is just 100%, I forgot to write that percentage. So any issue up to this point? If you make any mistake, you know what where your mistake is.
What is it?
100%. Yeah, for the 100%, just change it 100%. Okay, so if everyone done, we move on to the next part. Okay, let's go back to the questions first. So now that we have the total mass and so 3 R's for the molar mass and the specific or gas constant for the mixture, and lastly the specific volume of the mixture. So actually specific volume of the mixture, never mind. Okay, so actually molar mass of the mixture here should be very straightforward because you just count you have the total number of mass. If you have the total number of mole, you can simply just divide the mass over the mole. So 32.2 would be the molar mass of the gas of the mixture. Then the specific gas constant is just universal gas constant divided by the molar mass. That's all. Okay, so the last part is to find the specific volume of the gas, right? So anyone has any idea how to find the specific volume of the gas? Yes. Again, if you don't know what to do, these are the gas equations. Or actually, since you are looking for specific volume, it's actually just PV equals to RT. Okay, because you don't even need the M. So from here, the question already gave you the P, gave you the T, then R you have just found it in the previous section. So you sum everything in, you get specific volume. Okay, so the T and the P are given in the question. So 1 bar and 15 degrees Celsius. So temperature, remember to change to Kelvin. Then 1 bar is converted to kilopascal with 100 kilopascal. So cool? Everyone understand this? You will notice that here mostly everything revolves around these few numbers. So you just need to be familiar with them to know what equations are available to you. Okay, then we move on to example 2. Anyone still have any question for this? 3, 2, 1. Move on. Okay, so example 2. A mixture of H2 and O2 is to be made so that the ratio of H2 and O2 is 2 to 1 by volume. Calculate the mass of O2 required and the volume of the container per kilogram of H2 if the pressure and temperature are 1 bar and 50 degrees Celsius respectively. So again, we have this same property. Take the molar masses of hydrogen and oxygen as 2 and 32. This one, yeah. Okay, so what the question is asking for here is, so you have a mixture of H2 and O2. Ratio of H2 and O2 is, so it's by volume or rather by mole, same thing. So let's say I use by mole. 2, O2 is 2 to 1. So you need to find the mass of the oxygen per kilogram of H2 and also volume of the mixture per kilogram of H2. So you can see here, okay, so this is one example where you really you are not given the number of mole or number of mass. So this is where you can, the question asks you to find per kilogram of hydrogen. So if you want to avoid it being a bit messy for you, you can just say that at the start of the question, you are solving this based on 1 kilogram of H2. Then that's all. Then you can keep writing the per kilogram or like the per kg H2. Because here you have two mass, right? You have kg of H2, you have kg of O2, which is a bit confusing. So just sub this one as one. Then that's pretty much it. Then after, of course, at the end of the question, you should be referring it that this is per kg H2. Alright. So I did say just now, if anyone is free, you can try this off. Did anyone manage to solve it? Or try this? Okay, so now pretty much what I wrote here, right, kind of gives you a slight hint of what you get. Because we say that you want a volume of H2 to O2 is 2 to 1. And we know that by volume and by mole is the same thing. That's why I read by mole, right? So since you are assuming 1 kg of H2, then from here, actually you can find mass of O2, right? Because if you are assuming 1 kg of H2, right, it also means that you will have 2 kg of H2 here. Like this is 2 to 1. So then it's just 1, no? Like, never mind, let's see what we show here first. So ratio of H2 to O2 is 2 to 1 by volume. So A is the assumption. So let the mass of O2 per kilogram of H2 be X. So for 1 kg of H2 that you have, we have X amount of O2. So see here, we are just giving it a variable so that you have something to solve. So like I mentioned just now, so if we know that, so if we assume the mass of the H2 is 1 kg, so which means that the number of mole of H2 is 0.5 kilomole. Right, so here, so again, this one we are assuming, we are letting H2 become 1 kg. So we can sub 1 here, 2, so number of mole of H2 is 0.5. So based on this, so then for mole of O2, you just say that MO2 is X, so the molar mass is 32, you sub 32 in. So this one is actually more towards playing with mass. The example here actually a lot of this kind of mass thing. Okay, so we know that volume of H2 over volume of O2 is equal to mole of H2 over mole of O2, like I said just now, equals to 2. So can you see how to solve it? Pretty much done. Because you can just sub 0.5 and also X over 32 into this equation. So then mass of the oxygen per kilogram of hydrogen is 8 kg. put this here. Sorry, put this here. Put this here. Then we will solve oxygen. Is next. So this is also why I always stress whenever you solve thermo, actually not just thermo, a lot of other courses. You write down everything you have first. Somehow when you write it down, you can see that the solution is really there. Okay, speaking of this, I maybe give you a slight tip for your next semester, not this semester. When you go to heat transfer, right, try not to forget your thermo. The basic thermo, not complicated. Because last semester, one of your senior did, not to say complain, he was telling me that the heat transfer was very hard. Then he showed me the question that he never do. Then when I look at it, I told him, this is actually just thermo. Then I told him, then he's like, oh, is that easy already? Because he forgot already about my thermo. Okay, so try not to forget. Because the basic is still there. You don't need to remember the complicated one, but the basic one, you can still remember. Okay, so we solved the oxygen mass now. We of course still have one more question, which is the volume of the gas, I think. So here we can find here we find the number of mole of the mixture first. Why? Because if you think about it, the next one that we need to find is the volume of the mixture per kg of H2, right? So we need to find the volume of the whole thing based on this. But so to find volume again, like I always say, if you don't remember what to do, you always do PV equals to MRT, right? But if you use this equation, you will have issue because you need to find this. Okay, because R is different for different gases. You need to find R for mixture. So in order to avoid that, then we use this version instead. So for this version, then you need to find the total number of mole first. So once you found the total number of mole for 1 kg of H2, then then you can use PV equals to NRUT to find the volume. Alright, everyone clear here? For this question? So again, these two equations, these two PV equals to MRT and PV equals to nRT, they are actually the same equation. Okay, just one is mole, one is mass. So whichever one is more convenient to use, just use that. They are both applicable. The mole version is easier because R value is just one value. The kg version, different based on different gases and mixture for R. Okay, is it okay if I go to next example? 3, 2, 1. Okay, I will only discuss one more example here, which is example 3. So this one is a hard one, if I remember correctly. Alright, so I will discuss this together with you. Let's look at this question. So we have a vessel which contains a gaseous mixture of composition by volume, 80% H2 and 20% CO. It is desired that the mixture should be made in the proportion 50% H2 and 50% CO. So you have a vessel. Let's say initially you have 20% CO, 80% H2. It is desired that mixture should be made in the proportion of 50% H2 and 50% CO. By removing some of the mixture and adding some CO. So you want to add CO such that at the end of the day you get 50, 50. So calculate per kilomole of mixture. So we assume the whole thing is 1 kilomole because here we say calculate per kilomole of mixture. The mass of the mixture to be removed. So what is the mass that you want to remove? And the mass of CO to be added. The pressure and the temperature in the vessel remain constant during the procedure, so we assume no change in temperature and pressure. Take the molar mass of hydrogen carbon monoxide as 2 kg and 28 kg per kilomole. Alright, so the complicated part of this question is this. Very straightforward at the start where you have different mixture, so you want to add CO until you come to 50. But when you are removing since volume is going to be constant, because temperature and pressure is constant, meaning volume will be constant. Alright? The volume will be constant. It means that whenever you remove the mixture, you are removing both CO and H2. You are not just removing H2 and adding CO. So that is the complicated part. So when you remove the whole thing. But when you add, you're only adding CO. So we need to do some math here again. Okay, let's see how we do this. So since pressure and temperature remain constant, the amount of substance in the vessel remains the same throughout. So we are saying that the mole is the same. The total mass might not be the same, but the mole will be the same. Because again, PV equals to NIUT. So this is a constant. If this is constant, this one will be a constant. Okay, the whole thing is constant. So therefore, the amount of substance of mixture removed is equal to the amount of substance of CO added. Do you understand the last sentence? So the mole or the volume of the mixture that you remove will be equal to the amount of the volume of the CO that you're adding to the system. Meaning, let's use that our Milo. You make 1 liter of Milo. Now you want to make a Milo not as thick by adding more water. But you don't have enough space already. So you pour out, let's say, 0.2 liter of the Milo. So that the whole mixture you are pouring out. Then you are adding 0.2 liter of water. So the amount that you pour out here will have to be the same as the amount that you add in. But you are not adding it back the mixture, you are just adding one thing. But when you remove the whole thing. Okay, so that's what we are saying here. So, once again, we do math. So we give it some variables here so that it's easier for you to visualize. So we let x kg of mixture be removed and y kg of CO be added. So why is it that just now we say they are the same, but here we give them different variables? Because here we are talking about mass. What we are saying there is the mole. So like I said, like the example that I give just now also, it will not be the same weight. Because you are removing the whole thing, but you are only adding in water. But the volume is the same that you remove. Or the mole. Mole is the volume in a sense. So here, for the kg that we remove, we put it x first, and y, we let it be CO. So based on this, because ultimately the answer that we are looking for is the mass. Right? That's what the question asks for. Alright, so now we look at the mole first. As you know, we find the molar mass of the mixture first. Because in order to convert these to mole, we need the molar mass. Right? So we find the molar mass of the mixture first. So to find the molar mass of the mixture, we use the mole fraction that was given to us earlier. So we know that there are 0.28% of hydrogen, 0.2% of carbon monoxide. So the molar mass to be 7.2. So that is the molar mass of the mixture initially. Okay, then from there, you can get the number of mole of the mixture removed. This is mole, okay? When we say amount here, we are always talking about either volume or mole. So here we are talking about mole here. So X was the kg removed. So we use X divided by 7.2. So this is the number of mole that we are removing. And the amount of CO that we add is Y over 28, same thing. And which means that they are equal to each other. So this is our first equation. Anyway, this is considered complicated. You understand so far? Up to this point. Okay, everyone still need this slide? Okay, if not, I move on to the next one. So now, so we established our first equation here. Then now we proceed to the next one. Alright, so okay, so now we look at the amount of H2 that we have removed from the mixture. So how do we determine this? So when we remove the mixture, we assume that we are removing the whole thing as a whole. So it is assume that it's well mixed. So it is still 80% H2, 20% CO when you remove them. So we remove X over 7.2 amount. So if we multiply this by 0.8, that will be the amount that we remove from the mixture. Right? Remove the amount of H2 that we remove from the mixture. Of course, you can also determine the amount of carbon monoxide that you remove, but that will not be useful because ultimately you are adding back CO, right? But calculating the amount that we remove from H2 is useful. Why do you think that is the case? Because ultimately we know that we remove 30% of the liquid, right? So now we do the other way around. So amount of the H2 where remains. So if we remove that much, this is the amount that is remain. Because originally 0.8, so now we minus back the X over 9, that is the amount that remains. Okay, so we are saying that so 1 kilomole of the new mixture is 50% H2 and 50% CO. So therefore, we know that the amount of H2 that remains is 0.5. Make sense? Then you can find X over 1, you can find X, you can find Y. So this. We're solving this whole thing based on 1 kilomole. Anyone needs more explanation here, please let me know. I'll stop here. The rest of the example we'll discuss tomorrow. Anyone needs more explanation for this question? This is next. This is next. Okay, so anyway, just confirm you guys. So the next Tuesday's replacement class I will just put on Wednesday, 11 to 1. Okay. Anyone here still read the code? Okay, if you don't have any other questions, I need to go now. Okay, bye-bye.
Thank you, sir.
This
Sorry lo. Okay, good to go, sir. Thank you.
Okay, so example 3 is actually an approximate breakdown of the air composition. Of course, we know all those very little composition. So here you are actually asked to find the specific gas constant and the molar mass for air. So in this case, right, you actually do know what is the specific constant of air as well as the molar mass of the air. So these things are given in the table. So in a way, it is just to show how we actually get these values based on the composition of air. So for air, the mass analysis for air is actually 23.14% oxygen, 75.53% nitrogen, 1.28% argon, and 0.05% carbon dioxide. So as the mass fraction is basically in this manner. So you can see that the carbon dioxide percentage is actually very low as well. Okay. Alright, so now the table at the bottom is actually quite nice because it does give you, it even give you the volume percentage. Okay, so based on what you learned yesterday, when you see this, right, you should also know that it should come to you that this is actually by mole. By volume means by mole. It's the same thing because we said yesterday or even just now. So pressure fraction, volume fraction, they are all mole fraction. So when you see by volume, you don't need to be confused. It is by mole. It's the same thing. Okay. So here this question also gives you the molar mass. Of course, the common value for molar mass that we use to be 32, 28, 40, 44. So those we usually use the round version, the round value. Okay, so for this question, we need to calculate the specific gas constant. So the R as well as the molar mass of air. So either way, for this question, you can actually find it either way. Like you can actually find it from the gas constant first, then molar mass, or you can actually find the molar mass first, then only the gas constant. It doesn't really matter because both they all just come from the same equation. So maybe now we look at how we solve here. I think this one we will need because even though the question says gas constant and molar mass, the first method that comes to my mind is also to find molar mass percentage because we know that R is equal to RU over molar mass, right? But let's see here. I actually find the gas constant first. So never mind, we see the gas constant method first. So here, based on the gas constant method, how can I do this? Now, this mass fraction and mole fraction, they are useful in the sense that basically depending on what you use, the composition and the properties actually go hand in hand. So for example, like what happened here is basically this. So now we want to find the gas constant of the mixture, right? So we know the individual composition of the gas. So we know that by mass, 23.1%, 4% is oxygen, 75.53% is nitrogen, 1.28 is argon, and 0.05 is carbon dioxide. So let's say if you go to the table and get their respective gas constant. So these are their respective gas constant for oxygen, nitrogen, argon, and CO. And you just multiply by their mass fraction. You will get the specific gas constant. Okay, this one is from the table. Sorry, wait. I just realized the order of this slideshow is a bit, the slide is a bit off. Okay, so you can actually find the respective R from here first. So instead of going to the table, to find the respective R, you can just use the universal gas constant divided by their respective molar mass. So all these values were from the previous table, so you need to go to the values from this table. Okay, so then after that, once you have the R, then you can just use molar mass equals to IU over R, then you can get the molar mass of A, which is approximately 29. So note here, when the approximate analysis for A, 23.3% oxygen and 76.7% nitrogen by mass is used, it is usual practice to use R as 0.37 and molar mass as 29. So these are the common value for A. Alright, now, so just now actually for me, the method that I showed just now is a little bit more complicated. Personally, what we would like to do is would actually be this. I'll do it the other way. So we know that molar mass is mass total mass over total mole, right? So based on the, but this will require a bit of assumption. So based on this one, let's say molar mass mass. Okay, so this one might be okay, maybe a bit more confusing. Let me think. So for example here, let's say we assume that the total, so we assume, for example here, we assume that we assume 1 kilomole of air or 100 kilomole, doesn't matter. Let's say if you assume 100 kilomole of air. So meaning you will have 20.95 kilomole of oxygen and then 78.09 kilomole of N2, 0.93 kilomole of argon, and also 0.03 kilomole of CO2. Right? So then from here, you can find how much the amount of mass that you have for each of them. Right? Because now that I assume this 100 kilomole, you can find the total mass. So then from here, if you come back to here, so you just use the total mass over 100 kilomole. So this way, then you get the molar mass of the mixture. Then R, you can simply just use RU over, and then you will get the same answer. See what I'm trying to say? Personally, I find this easier compared to the previous method that I showed just now. Because this method doesn't require anything too complicated. You assume a certain amount of mole, find their respective mass, then you divide, then you will get the molar mass. Okay, you guys understand? Do you get like so both methods? Anyone that don't understand both methods? Okay. This second method that I introduced is pretty straightforward actually. You just use the standard molar mass method. So total mass over total number of mole. But of course, based on the question, you have no idea what is the mole or the mass because all you have is just the percentage. So we assume a certain percent of the mole, then we find the number of mass. Or you can also do the other way around. You assume a certain amount of mass, so 1 kg let's say. Then based on that 1 kg, you can find the respective mole. So after that, you just need to divide. So like in this case. So either you assume 100 kilomole or you assume 100 kg for example, or 1 kg. Then you divide by the mole. You use either one of them to find the other counterpart. Then from there you can get the molar mass. Then after that, it's just the application of equation. So the method introduced by this question instead is basically this. This is the gas constant for the oxygen. If we have 1 kg of oxygen, this is the same thing. So gas constant of nitrogen for 1 kg, 1 kg, 1 kg. But in this case, we don't have 1 kg, right? So for air, let's say if you have 1 kg of air, you only have 0.2314 oxygen. Only have 0.7553, etc., etc. So basically, you just break them down into the respective fraction. Then you add them out. Then this is the gas constant. So you can actually do the same thing for mole as well. Actually, mole is even easier because for mole, wait, can you do that? Okay, no, I think in this case we can bring mole because the mass makes more sense. Because mole doesn't make sense since IU is the same anyway. Okay, so this one is basically just breaking them down. So if you have 1 kg of oxygen, that is the value. 1 kg of nitrogen, that is the value. But in this case, what you have is 0.2314 kg of oxygen. So you fraction out the properties. So you total them up, you get Rm. Then you can use the R or Rm here to get the molar mass. So what I did, the second method I showed is the other way around. You find molar mass first, then you can find R. Okay, so we continue from example 3. So calculate the analysis by volume and the partial pressure of each component when the total pressure is 1 bar. So this one actually is quite straightforward as well. So we have mass 1 kg, we know the mass fraction of each of the oxygen. We know the molar mass of each of the oxygen. So then, let me check that paper. So now, actually this is where we are assuming 1 kg. So like in this case, right, we assume 1 kg of the mass. So that we convert this mass fraction into kg instead of just fraction. So now, if you assume 1 kg of mass here, so you have 0.23 kg of mass oxygen, of nitrogen, argon, and carbon dioxide. Then based on their molar mass, you can convert them into mole. Okay, so then here this mole, you total it up, you get this value. Then you find the mole fraction. So of course, this mole fraction value is actually given in the table in the previous page. But I think this was just a summary now. Because here, if you read the question doesn't give you the mole analysis, but the table does give you. So actually, you check this value by volume percent, you will see the value is the same as what you calculated here. Okay, so this is the way that let's say you do math. So this is also what I mentioned just now. So you can actually, so for like this question, right? You total them out, you get 1 kg, right? So you use 1 divided by this, you will get the molar mass value just now. Okay, so once you found the mole fraction, then we know that Pi over Pm, so the individual pressure is equal to the over the mixture pressure is the mass, the mole fraction. So you are asked to find partial pressure, which is this value. So which means it is as simple as this, because the pressure is 1 bar. The final pressure is 1 bar according to the pressure. Okay, so let me move on. Any questions here? Okay, so now we look at a new law. Actually, it's just a new name now. Nothing too special here. So let us see. So now we look at what we call Gibbs-Dalton law. So the internal energy, enthalpy, and entropy of a gaseous mixture are respectively equal to the sum of the internal energies, enthalpies, and entropies of each gas. So each gas has an internal energy, enthalpy, and entropy, their volume occupied by the mixture and the temperature of the mixture. So actually this whole thing is the same as what you saw just now, but now we move it to internal energy, enthalpy, and also entropy. Right, so we just jump to the next slide. Sorry, not next slide, so the diagram. Okay, so what we see here is very simple. The total internal energy or the mass, the mixture, is just the sum of each of the gas, the internal energy of each of the gas. So this one makes sense, right? So we also learned that we have a small value, so it will equal to the mass multiplied by the internal energy or the mole multiplied by the what is called. But anyway, if you have a bar on top, it's in per kilomole. The normal one is per kg, this will be per kilomole, but otherwise it's the same thing. So enthalpy same thing, entropy is the same thing. Alright? So which means, let's say you have this, very straightforward. If A you have 2 kilomole, B you have 6 kilomole, but UA is 1000 kilojoule, UB is 1800 kilojoule. You don't care about mole, you can just total them up, you get 2800, the internal energy for the mixture. So because they are the extensive properties, so you just add them up. But what if what you have here is based on per kilogram or per kilomole? Then you see that here we need to include the mass and the mole. So which is here. So here, if A is 500 kilojoule per kilomole, B is 600 kilojoule per kilomole, then you need to make use of the number of moles here. And in this case, you need to make use of the 100 kilomole by using the mole fraction like just now. So you can see that this is not a straightforward 2 multiplied by 500, 3 multiplied by 600, because this is definitely not the answer. So you need to make use of the, so in this case, right, what you are doing here is, so 2 times 500 plus 3 times 600. This is exactly the same thing that we did just now for the gas constant, the specific gas constant. So now we are doing the same thing for, like let's say, internal energy, enthalpy, and also entropy. So it has to be the fraction, not the normal value itself. So this, no, sorry, let me rephrase a bit. Because here, the reason we need to use the fraction is because here we are looking for the mu in terms of per kilomole. If you are looking for this in terms of per kilojoule, yeah, you just multiply and do the same thing. Okay, but to find the mu in terms of kilomole, then yeah, you need to use back the mole fraction. here we just talk a little bit about what you saw just now. So expressing the internal energy, enthalpy and entropy of a mixture per unit mass or per unit mole are in this form. So yeah, so this was what we did just now. So let's say if you are looking for the internal energy per unit mass, then you use mass fraction. If you are looking for it in terms of per kilomole, so like we did just now, you use the mole fraction. So the 205, 305 just now were mole fraction. Then yeah, enthalpy and entropy, same thing. So similarly, let's say if you want the new specific heat of a gas mixture, it's the same thing. Okay? So we want a specific heat of the mixture, so this is the specific heat for constant volume. Then per kg you use mass fraction, per kilomole you use mole fraction. So you can see we use the same equation here. So since Cp minus Cv equals to R, so Cp minus Cv equals to R, so this also equals to mass fraction multiplied by gas constant. So again, this was what we did just now in the previous example. So you can do the same. So it actually, it looks like there's a lot of things. Actually, they are all the same method, regardless whether you are taking it specific internal energy, enthalpy, specific heat, specific gas constant, all same method. Just different things. Okay, so we also, lastly, we know that K equals to Cp over Cv. Yeah, this one no shortcut, you just find Cp, find Cv, divide, then you can get a K. Okay, so specific heat capacity Cp. Oh, sorry, oh, so that's the thing. So specific is for the unit mass, right? So molar heat capacity is the one in terms of mole. So specific heat capacity is the amount of heat required to raise temperature of the unit mass by 1 Kelvin. So molar heat capacity is the amount of heat required to raise the temperature of the unit mole by 1 Kelvin. So this one is the same, okay? So the logic behind it is still exactly the same. It's just that, so if you want a Cp bar, you multiply Cp with the molar mass. You want Cv bar, you multiply Cv with the molar mass. Then Cv minus Cv gives you R, right? So Cp bar minus Cv bar will give you universal gas constant. So you can see the relationship is exactly the same, whether it's mole or mass. So here, so same thing. We know that internal energy is mCv delta mCvT. So let's say if you have Cv bar, then you multiply by mole instead. Same thing here. Enthalpy is mCvT. If you have Cp bar, you multiply by n. Number of moles. Okay. So to convert Cv to Cv bar, you just use same thing. You use the mole fraction here. And Cp also same thing. Okay, then lastly we look at entropy. This one I'm just showing you. I don't think anyone will remember this equation because I also don't remember. So, not sure if you remember, but entropy we use this equation as well. So we actually have this equation. Delta S equals to S. I don't know what to call it. S is the degree. The difference minus R ln T OT. So which is approximately Cp ln T and minus R ln P. So by then we do have this equation. So this equation, we can also change it to the mole version. Cp bar IU. Again, same thing. You just replace the mass counterpart with the mole, the mass with the mole counterpart. And pressure here is just this. Now, for the entropy one, you don't really need to worry much. I don't usually ask about entropy. The most also, I will just ask you take this equation, apply it. Okay, so for this equation here, we are just showing you how to get these two. So these two values are the partial pressure of component I at state 2 and partial pressure of terminal at state 1. So this will involve process where the state changes. So you can see that the P here will be the partial pressure. The T is also the individual temperature before and after. Yeah. So the most, like I said, the most that I will ask you to do is take this equation, apply it. That's all. Alright. So for this chapter, pretty much everything that you need to learn you can learn that. So now we look at the next slide where I will show you some examples of how we make use of this equation. And also, the examples in this slide are actually considered hard questions. So if you cannot do them or you cannot understand them, it's okay. But they are considered hard. Come from the previous lecture. Okay, this chapter actually I also don't like. Okay, so all the examples are in this slide. Now we look at example 1. Example 1 should be something that you can do. Let's read it first. A mixture of 1 kmol CO2 and 3.5 kmol of air is contained in a vessel at 1 bar and 15 degrees Celsius. So you have one vessel, you know that inside you have CO2, you have air, and you know the pressure temperature. You are given volumetric analysis of the air. So this is actually quite similar to one of the examples we discussed yesterday. So here you need to calculate the respective mass for CO2, O2, and N2, and then total mass. After that, calculate the percentage carbon content by mass. So based on this total mass, how much carbon do you have? So it's not the mass fraction for carbon dioxide, oxygen, or nitrogen. It's the carbon. It's the mass fraction of the carbon. Then the molar mass and the specific gas constant for mixture, specific volume of the mixture. So you are given the molar masses of carbon, oxygen, and nitrogen as well. So these examples should be one that you can do. So try out based on what you learned just now. What is it there?